So critical angle, we decided, was the first angle where no refraction happens. So when you pass light through a particular medium, it changes direction. It changes direction because it's changing speed and it's also changing wavelength. So when this passes through here, there's an angle within that medium, and that angle in air is always greater than this angle in the medium because it's speeding up as it emerges into air. So what we did in our experiment was to vary theta in the medium, increase it, and observe what happens beyond refraction. So around about 20 and 30 degrees, we didn't really see anything unusual happening. We would have had an angle here that was larger than this angle within the medium, and we probably wouldn't have seen really any sort of reflected rays that we could measure. Around about 40 degrees, you will start to see a reflected ray appearing, and then 50, 60, 70, 80, you should see no refraction happening whatsoever. Last of all, we measured the theta in the medium when theta in the air was 90 degrees. So in other words, it would look something like this. You've got your normal line, and that's passing through. You're looking at something like this. It comes out like that, and this should have been, I think we figured out, around about 42, 43 degrees. So that is the point at which, beyond that point, no refraction happens. This angle here, this is your critical angle. That's the angle beyond which no refraction occurs. So by refraction, I mean light passing through the other side. So you would expect from our previous knowledge of refraction and refractive indexes that this light will pass through the prism and it will pass out the other side. We can predict the change in direction, we can predict the wavelength change, we can predict the speed change from our refraction formula, or extended refraction formula, but this is a different scenario. This is where the light starts to bounce back, and when it bounces back, we should find that, say, the theta in the medium, the reflected ray will be the same. So if this is at 70 degrees, the reflected ray will also be at 70 degrees. So we use this animation just to kind of tie that in. This is round a slightly different way, but works in the same fashion. So for small angles, we've got a larger angle out the other side due to the change in speed. Once we get round towards 40 degrees, we're starting to see a brighter reflected ray. So that begins to appear, and then at 90 degrees, that's your critical angle there. So 42 degrees here for this particular animation. Beyond that 42 degrees, once you get past 90 degrees, this refracted ray moves round to here. So 43 degrees is your angle in the medium there, and then 43 degrees is your angle of reflection. And that will hold for any sort of angle, so 68 in, 68 out, and so on. So in summary, we increase the medium round like this. As we do that, we start to get a brighter reflected ray, and we start to get, this becomes dimmer and dimmer as we move round towards this 90 degrees. At that 90 degrees, we come up with a critical angle. That's the angle at which no refraction occurs. When theta in air is 90 degrees, refraction stops at that critical angle. This reflected ray is much more intense because all of the light is reflected back to that, and that's when internal reflection happens. So we're looking to use that knowledge, the fact that the critical angle happens at theta equals 90 degrees in air. We're looking to use that knowledge combined with what we had for refractive index before to figure out a new equation for the critical angle. So n is, this is the formula part, n is equal to sine theta in air divided by sine theta in the medium. The less dense material always goes on the top of the equation. In your data booklets, that will be written as sine theta 1 divided by sine theta 2. But for total internal reflection, which I'll just denote as TIR, sine theta is equal to 90 degrees. So that's the sine of 90 that goes on the top of our equation here, because that's the less dense medium. So sine 90 degrees divided by sine theta in the medium. So we end up with n being equal to 1 over sine theta in the medium and that's when we need to look at what sine theta in the medium is at that point in time. What is this angle down here when this is 90 degrees, and the answer to that is the critical angle. So we can say that the theta in the medium here is, we could call it theta c, or we could call it c. I'm going to call it theta c here. So therefore we end up with n is equal to 1 divided by sine of the critical angle. And that is how the critical angle relates to our refractive index, and that's the equation that we'll use when we're trying to perform calculations on the critical angle. So if we know the refractive index of something, we can figure out what the critical angle is. If we know what the critical angle of something is, we can figure out what its refractive index is from this simple equation. So it's just another tool that we can use to solve problems with light or with waves passing through